So there's my screen. Oh, yeah, great. Cool.
Amy, is it possible to mute the non-speakers?
Yeah, let me see. Oh, mute all. And mute.
Okay, so I'll start. Okay, I'm going to talk about making tables with the GT package. So let's get into it. Let's look at tables in general. So this talk presumes that you haven't heard of GT or even maybe a table before. So let's go to the very beginning here. Let's look at the most useful features of a table. So here's a table. It just so happens it was made with GT. Let's forget about that for now. Let's pretend it's just a table that we found somewhere. When I started making GT, the first thing I wanted to do was plan things out, understand what parts of a table should be called, what their use is. It's basically trying to find the function of each part, and eventually build an API around that. But first, we want to identify things and see what their purpose was. Things that are common, things we see all the time. So the first thing I see all the time is like a table header, just a title, sometimes a subtitle, goes at the top. Very useful. I'd say most tables that you see have a title. This is an interesting one. It just seems like another column, but it's like the leftmost column. Sometimes there's a label above it, sometimes there's not. Sometimes they're just labels for data. They don't actually contain numbers. They're just like almost like column labels, but they're row labels. In GT, we call this a stub. It's kind of a strange name, but it's actually a historic name from the US Bureau of Statistics that they used a long time ago. So we decided to keep that. It's kind of a cool name, and it's very short. Column labels. These are always in tables. They label the columns. Sometimes we have multiple labels on top, spanners. In this case, we have one spanner above called performance, above 3 different columns. So column labels, they can group columns. And data formatting, that's kind of like a feature of a table. Like surely this data doesn't come in like this with $signs and all as text. It's probably like modified in situ essentially. So that's called data formatting. And footnotes, very common in tables, especially in like journal articles and other places like that. So, and I noted down here in the right order. That's kind of a key thing. They're always in the right order when you see them printed. And if you want to make our own tables, we got to make sure they're in the right order. And a source note. So that's basically a note that's about a table. It doesn't refer to any specific location on the table. It's just about the table in general. It could be like the source of the data. It could be about anything. Great. So those are the main features. I just want to draw your attention to footnotes and the fact that they must always be correct, the ordering. And if you ever had to make a table and put in little footnote numbers and the data changes or you move columns around, you have to change the numbers yourself, that's really no fun. So if you're going to build an API that does footnotes, we never want you to manually get in there and like write the numbers or have to specify where they live. The API should handle that for you. Okay, and to do that, we have to essentially number all the different locations where footnotes could be. So it's essentially like an index. It needs to go from like left to right, top to bottom. So here we have 80 locations for footnotes. And that's really simple because we can even have footnotes inside cells. Like say, for instance, there could be a footnote on 6-speed and a footnote at the end of manual. And that's a very specific ordering in itself. So the system has to be smart about the formatting of footnote marks too. So you have a situation where you have a 1 and a 2, like there might be multiple notes for one location. So these are all little considerations that went into like the planning. So the GT package, it essentially formalizes the parts of a table. And we call them just parts. We can call them structural parts, but because they add structure to a table. But let's start from the beginning here. So this is a very simple table. It has column labels, a few columns, a few rows. Intersections of columns and rows are cells. The cells are in the table body, and the column labels are in the column labels area. So that's the most basic form of the table. And you see in the last sort of like example table, we could have the stub area. and they serve as like row labels. You don't have to have it, but sometimes it's useful because we can actually refer to like those labels for ways of targeting cells. They become almost like columns in that you can use them. And we do that through tie select internally in the package. And you may have a stub head label, which goes in that sort of the top left position. So that's an optional thing. There's actually a function just for setting that label. Okay, and you may have groups of rows that are important. So we can create a row group, give it a label, and this label can actually span its way across the table into the field, like into the table body if you wanted to. Here's just to the left, but in essence, there's no cells here. It's just essentially this is the label that tells us that all these rows belong to a certain group. Okay, and for different groups, we can have summary rows. So this is great if you want to have things like sums or statistics here that refer to each column. And it could be one or more columns. It doesn't have to be all the columns. It could just be a few. And these summary labels or these summary rows could be group-wise, or they can exist for the entire table, or we can have both. Okay, here's the title and subtitle. It just goes into the table header section, which is great. And at the bottom, we have footnotes and source notes. That goes into the table footer section. Okay, and we can have spanner column labels. They can be above certain column labels. You don't have to have them in all of them. You can have multiple of these. It's a really great way to sort of delineate or sort of create some structure in your columns. Great. So that's all the parts of the table that we care about in GT. Let's actually learn how to use GT. So the GT package comes with a bunch of datasets. I really love datasets. They're like it's like one of my pastimes is creating datasets. It's kind of a weird thing. Don't ever get into that. It's a strange thing. But we're going to use a really boring dataset for GT, in GT. It's like the least interesting one, but it's the most useful one because it's only a few rows and we can fit it all on the screen. We don't have to do any sort of pre-processing with it. And it has a bunch of different types. So this is essentially the table right here. So the very first thing you need to know when using GT is to use the GT function. It's kind of like ggplot. You have to use a ggplot function. So if you introduce any data table to GT, it just makes that table with a bunch of defaults, like it'll automatically align columns, it'll make an HTML table, it'll print it in the RStudio viewer, stuff like that. So that's what this table looks like. And nothing's been formatted. As you can see, this is basically just like running all the values through R's format function. Okay, now there's different families of functions. We have like this family called create or modify parts, and there's a bunch of functions in it. I'm not gonna go through all the functions because there's almost there's more than 80 functions in the package, so I'm gonna show a few here. But this one's a great one. This creates a title. Easy to use. All these functions start with tab. You just do the usual, get the exhibit table into GT, then tab header, and give it a title. The first argument is a title. And you can use Markdown. Just use MD helper, and you can use Markdown there, and it bolds this GT. So that's pretty cool. Here's another one, tab source note. This creates a source note. Again, you could use Markdown if you want, but we're not using it here. We're just saying from GT, and it appears down there. So these other functions, I'm not going to show you what they do, but I'll show you that in the demo later. But what this does is allows you to add styles to any targeted cells. This allows you to do sort of table level operations, like radically change the look, add colors, change fonts, stuff like that. Okay, formatting data. This is a really important thing because if you ever formatted numbers in R, it's very difficult if you use sprintf or format C. It's hard to get the thing you want, but in GT, it's pretty easy. Use format number if you just want to do a number formatting. And there's tons of arguments, but we're just going to say, show the decimals 1. Put decimals 2, and we're guaranteed to get 2 decimal places. And NEs are untouched. So scientific notation, really great feature. It's hard to get it right. There's lots of little exceptions here and there. But if you just pass this through scientific notation, like format scientific, and we specify the column through this bar's num, it's this column right here, we do get scientific notation. And we're careful not to have anything times 10 to the 0. So scientific notation requires you to not, sort of discourages you from having that sort of weird notation there. Okay, currency. there's lots of currencies in the world, but this format currency function handles all of them. Like, I'm pretty confident. There's about 180 different currencies in this package. And it knows things like, the marks for the currencies, and it knows how many decimal places there are, things like that. And also, each of these functions has a locale argument. So if you're in a place like, well, say in Switzerland or Spain, it'll show commas here, or even spaces, depending on where you are. So it's locale specific if you want it to be. You always have to opt into a locale thing. So dates, you can format dates. The only thing you need to have is a date object or some string that's already in ISO notation for dates. And then you can just easily use this date style, give it a number. If you want to know what these do, I would just use the info date style function. Shows you a table with all the different examples of how dates get transformed into different styles. I think it's just easier to have sort of like this, instead of having a description, which makes no sense. Okay, missing data. So we had a bunch of NAs before. We can do a thing. This is sort of like an afterwards thing. If you format a bunch of values, you can also use format missing. You can choose what to target. In this case, we're targeting everything that's NA and replacing with the default replacement, which is an M dash. We can choose what to replace it with and where to replace it. So it's kind of nice. You can target the missing replacements. So with multiple calls of format missing. Great. Whew. This is a lot of functions. Okay, but hopefully you'll not remember this stuff, but hopefully it gives you some idea what the capability is. That's really the point here. So there's a bunch of functions inside this modified columns family of functions. They all start with calls underscore. In this case, I'm looking at calls align. It just changes the alignment of values in a column. So in this case, these were formatted to be left, and I think this one was center. In this case, we're just aligning it to the right, these two columns, char and factor. Okay, sometimes you don't want all the columns that you put into GT to actually appear in the final table. So for that, we can use calls hide. And in this case, you might notice we're using matches. That's from dplyr and, and friends. We're essentially re-exporting all the tie select, or actually just using tie select, its functions to select columns and to choose which columns to hide. And you may ask, why would you hide columns? Why don't include them in the first place? Well, you can use columns, the data inside columns, to do conditional sort of expressions to format something based on some other column. Then you may, in the end, want to not show that column that you're using. So that's what this is for. Okay, calls merge. So that's taking two or more columns, merging them together, and then optionally hiding other columns. So in this format here, we're taking char and factor, so factor's gone. We're merging them together with this pattern. So this 1 refers to char, this 2 refers to factor, and see, we're putting it in like that. So it's kind of like a string pattern. And what this does is it automatically hides columns 2 and beyond. You can opt to not hide that column, but by default it does that. Okay, that's a lot of functions, and there's way more. As I said, there's like 80 or so functions. It's a little bit crazy, and they're all sort of broken up into these families right here. Create table. We went through these ones right here, very quickly, but there's tons more. The best way to learn about the functions themselves is to go, use GT, but also look at the reference here in GT RStudio. This is essentially the package down site for GT. It's all accessible through the README of the, sorry, I want to do that. The README of the package in GitHub. And there's actually a button you can press called GT Test Drive. It takes you to an RStudio Cloud instance, and you can actually try out tons of examples. All the examples for every single function in these families is available in R Markdown documents, and you can just play with them. And all you gotta do is have an account to RStudio Cloud, and you don't even have to install the package. It's pretty sweet. So I'm gonna go to a demo now inside RStudio. Hope I'm pretty good for time. It's not too bad. Okay, RStudio is here, it's GT. Here we go. So this is what I call a crazy example. I just want to show you what is possible. Try to show you something cool. I'm going to load a ton of packages. So GT, Tiver, Scale, SVG, yes. I love that too. Equation SVG, yes. So as you can see, we can do SVGs inside tables. Sometimes you just want to have these little graphical bits inside tables. And shout out to Emil Pelletier, that's getting the library treatment. So the first thing I'm going to do is create this nice equation. It's going to appear in the viewer. Essentially, this is an SVG version of this equation here. We'll stick it in the table.
Can you,
yeah.
can you make the code a little bit bigger?
Yeah, of course. Sorry, it's a little slow. Is that good enough, or should I even go a bit more?
I think this is good.
Yeah, yeah, it's a giant display. And, yeah, sorry. Okay, I'm going to create sun and moon SVGs here. This is from the OM SVG package, which is getting some line awesome icons. And if you ever want to see this, you just type in info line awesome, and we'll get a G table with a bunch of line awesome icons. You can anywhere. Easy enough to get them. You just do SVG_LA, and then the name of the icon, which is basically in here. And there's 2,000 icons in here, and they all look pretty nice. Okay, then we're gonna use Pelletier. We want this palette right here, this GTSci orange material palette. I'm gonna show you the awesome print method that Pelletier offers up. Fantastic, I love it. But I want, I want them as a character. I really want this in the end. Okay, cool. So we're gonna use a different data set, SEA. It's short for not what you think. Solar zenith angles, or angle. I'll show you the data set inside the console here. It's giant. It's basically, it's hard to explain. The sun has a certain angle based on the ground, based on latitude, based on time of day, based on month. And that's what this captured. We're gonna whittle this down to a smaller tibble right here. So it's gonna be like this. You can actually see it's only 12 rows at some latitude, some fixed latitude, which is 20 degrees north. Okay, it's gonna look much better as a GT table, trust me on this one. So I'll take you one bit at a time. Actually, let's do it like this. We'll run a bit of GT code at a time because we got the time to do that. Okay, so here's the GT table, just with the data popped in. We're calling month the row name call, so that puts in the stub. So it's set off, it's got a line here. It's treated differently, there's no column label above it. It's really a stub. We're gonna take these NA values and obliterate them. We're gonna put in empty strings. So I'm gonna run that bit of code. They just disappeared. It's kind of sweet because you don't want to see them. Okay, now I've got another function called data color. This is really neat. Essentially what it does is it applies color either to the text itself or the backgrounds. I'm not going to explain too much, but you're going to see a heat map of different colors here. And it's pretty nice. I think that's not the whole table too. It stretches out a bit more. There we go. Yeah, so basically it's 5:30 a.m. to noon. And basically, at noon, the sun is at its lowest angle compared to straight up in here. And this is, the sun is not even up yet. Okay, stub head, I'm gonna put in a label there. So you'll see it in the top left, just put your eyes right here. It has to run the data color code, which is a bit slower. It tells you it's the month and it's 20 degrees north. Okay, I'm gonna run the rest because essentially it's just more parts. It's like the header, the source note, and a ton of stuff to style a table. I'll show you this, it's kind of cool. And this is kind of using glue, HTML, and we're sticking in that SVG right here. So that formula just goes right in. It's kind of nice. There's a link here you can actually use. Look at this. These are SVGs in the, the title, sun and the moon. I love it. I don't know. I think it's a good looking table. I mean, it's nice. I would present this somewhere, if I was talking about SDA. Nobody ever talks about that anymore though. It's kind of a shame. But if you are, use this table. So that's about it. I want to open up to questions. I can definitely answer any questions you may have. And I'll leave my screen available in case you want to type in some code.
Kelsey asked in the chat, she wants to know about output functionalities, HTML, okay. LaTeX, PNG, like what are the formats?
Yeah. Okay, so I'll talk about that. Right now, GT is great for HTML. It's not so great for LaTeX. some early promise, but we were focusing more on the HTML part just because we wanted to get that done before we ported that stuff over. Otherwise, we'd be always switching between the different output formats and never getting anywhere, which is, kind of a tough spot to be in. The idea is to get it so this looks reasonably well in LaTeX. It uses enough LaTeX packages so we can actually do the coloring, all the different, font stuff, the styling, as much as we possibly could. But right now, it's mostly HTML that works really well. We can export it as PNGs, as PDFs as well. We do that through, I'm going to type it in. I believe it's GTSave. Don't remember my own functions. GTSave, and all you do is you put a file name in, so you just do SCA. Pardon me? Can you repeat the question again?
I think someone accidentally unmuted.
Oh, okay. That was my question. But if you want to see this as a PNG, you can do this. It does an internal sort of web shot, and it captures the table quite nicely and crops it. So it looks pretty good. It's reasonably high resolution as well, so it captures all the text pretty nicely. Unfortunately, we don't have things like capturing it as anything more high resolution than that, like SVGs or anything like that. We don't have a device for that yet. Yeah. Hope that answers the question.
There are some more questions. Mason asks, how does this integrate into R Markdown, and what are the advantages of this over existing table functionalities in Markdown?
Yeah, well, it integrates well. Like, there's a print method, and it will print the table, which is nice. The advantage of this, it just depends on whether you find GT easier to use or has better features than the other packages you may use. I'm trying to think here if there's anything that really puts it above and over. Well, as far as I can understand, like things like putting footnotes in tables, it's still pretty much a manual thing with other table making packages. I haven't demonstrated it, but if you want to put a footnote in here, it would be, tab footnote. And then the thing to do would be, say footnote. This is one thing you can't do in other packages. I mean, you can put footnotes in, but you have to say exactly where they go. But here what we do is in the locations argument, you would put in like a locations helper function. In this case, it would be cells body, for instance. And if you wanted to specify where you want them to go, say you wanted them to appear in these low numbers right here. So this is kind of a cool demo. Oops, sorry, just trying to see what the column name is. 1200. Okay, so we just say columns equals bars, 1200. And then we'd say rows, because we want an intersection, equals, I think it's going to be 1200. Can't type. 1200 less than 5. Let's see if this actually works. I guess I can just do it here. And so if I got the syntax right, my own syntax, yeah, I did get it right. It'll essentially say, like, in this column, any values which are less than 5 will get this one, it's the same footnote. And of course, you can also specify July as well. You just get the row, put that inside rows, or the number, the row index, like the number, if you know it. So lots of ways to specify where you want to target things. And I think that's not possible. Like if you switch rows around, like columns around, it doesn't matter where you put it in here. Essentially, it's fixed to the initial table coming in. So that's maybe one reason why you use this. In Markdown, it works. It just, if you prefer to use this package, that's, I guess, the differentiator.
I think you can do a lot more customization with this compared to Markdown.
Yeah, I want to call out, again, Malcolm's wonderful, well, stretching this out, that's fine. His post here, my giant Twitter window, which I stretched out. Essentially, this is what he did. And wow, I mean, is that New York Times or is that GT? I can't tell. So you can do other stuff. You can do you can take the table, make it raw HTML, further modify it with HTML tools, go to town with modifying HTML, and make a really awesome bespoke table. Yeah, I'm gonna put that back off this side.
Scott asked, how do you change font?
I'm glad you asked that. Right now I'm working on a PR, which does things like adding in Google fonts, which will be potentially super exciting because there's lots of great fonts there. But right now what you do is you can't set a global table font. That's what that PR will address. But you can use tab style like this. And it works kind of like this tab footnote. It takes a style. So I'm going to type in style. And then you would do cell text. And then there's a font argument. And then you put in like, comic, song, MS. And then locations. I'm just going to steal this location here since it's already there. And maybe this will work. Let's find out if we get some comics on. Yes. Yeah, there we go. That's changes in the font location. So you can do, multiple locations in a list right here. So it could be, oh, sorry, not there, in the locations part. So you can specify all of the, all of the body, all of the columns, the column headers, all of the title. But that's going to soon be easier with a global font that can be set in that PR. And you can use any sort of system font you have that you know the name of, and any Google font, which is really kind of sweet.
Next question. Can it be combined with plots via patchwork or calplot?
Oh, no, I can't. And Thomas actually asked me about this. He wants me to make this a table grob. And that would do it. And you'd have it combined via patchwork with tables and stuff. But I don't have time for that. I mean, I'm trying to do things like make RTF, and it seems nice to have it combined with ggplot. I love it, but I'm like the sole GT person. Yeah. It'll take some time. I know nothing about table grobs as well. So that doesn't help.
Any interactivity possibilities like DT?
Kind of. I mean, there's a thing you can do where you can have any HTML in any cell. So if the output context is HTML, and then you could just take any of these cells and put it in whatever web fragment you want. It's a little bit hard to do JavaScript though, because you'd have to do the HTML's root and get that, the script stuff in there. But you can have things like, SVGs for rollovers, anything that's CSS based, that's possible. So the function you use for that is maybe text transform. And it's a pretty powerful function. It seems like, pretty innocuous. Like, what do you do with this? Essentially what you do is you specify a place. You got the original text as X. You just remake X. You can either use X or throw it away and just add in something. It could be HTML. Well, it's probably gonna be HTML. It's gonna be some sort of like combined HTML and CSS if you want to make something partially interactive. And I guess if you want something like a small plot that can be rolled over, things like that, you probably do a combination of HTML and CSS, like inline inside that table cell.
I think he was asking more about like sorting, like how in DT you can.
Oh yeah. No, we don't have that. Not yet. That's the goal though. We're gonna get there. We're gonna have. That might be a while away though, is what I'm saying. So DT is not going anywhere.
Can you specify data color bars? I don't know what that means.
Yeah, you mean like, have a bar going across like a pretty wide.
Like
I mean,
I'm not sure what he means.
Well, if he means what I think he means, it's like putting bars across. There are certain lengths with colors. I mean, I see that in other table making packages. Again, we don't have anything high level that makes that possible. We don't have a format bar or anything like that yet. But I could potentially see that because the HTML to make that possible is pretty simple. I mean, you could probably find it just by going on Stack Overflow. I mean, I don't know it. I'm assuming it's simple because it'd be found there, and there's lots of examples. But yeah, essentially you can do that, but it's a DIY thing.
Final question: is it possible to include plot in a table cell?
Yeah, again with text transform, it's not fun or nice. There's examples that exist in a GitHub issue, and I think we have a branch that's been abandoned for a while to try to make that work. We sort of abandoned it for now because it was less important than other things. And also, we want to make it work for all types of plots. And there's lots of little considerations for making plots inside, table cells. You'll have tiny labels if you're not careful. So it seems like we need some sort of like set of geoms, or at least a way to sort of like create plots that work inside of tables. Yeah, and we also don't currently have a way to span a large plot across multiple columns or multiple rows. Like, for instance, take this, section and make that a giant plot. Yeah,
that would be cool.
Yeah, it's something we're going to work on soon, but probably not too soon. But it's definitely going to be worked on.
We have 2 more questions. Do you mind that we switch to Avik and maybe you can respond in the chat?
Yeah, absolutely.
Yeah, thanks, Rich.
All right. Thank you so much.
Great job.
Thanks.
Okay. All right. So let me share my screen and I will let you know what I'm talking about. Okay, so what I'm going to be talking about today is a computer science concept called dynamic programming. It's something that is often taught in school, but a lot of people don't really realize what it's used for. So when I was writing a blog post to help other people understand dynamic programming, this question came up. What is it used for? And I found some cool applications, including one I had also learned in school. I just didn't realize it was dynamic programming. So today we're going to cover something called hidden Markov models. I'm going to see how it's used and how we use dynamic programming to do things with these models. Okay. So let's see here. All right. So just so you know where I'm coming from, I work at LinkedIn. I went to UC Berkeley. I have a lot of mathematical background, and currently I write code. So I love to see the way these theoretical concepts get applied in the real world. They provide for a lot of cool insight. You might use things like hidden Markov models by importing some package, using some library, but it's really important to understand what's going on under the hood, so you know when these libraries are applicable and when they're not. So the goals we have for today, right? We're gonna introduce what are hidden Markov models. We're gonna see how dynamic programming lets us actually make use of hidden Markov models. And then we're gonna go over some real world usage just to see how hidden Markov models are being actually applied. So let's define what is a hidden Markov model. First and foremost, it is a description of real world phenomena using some symbols and numbers and equations. There are a few different parts to a hidden Markov model, all of which I'll cover in a lot of detail. But basically, there are things that are hidden from you. There are things that you observe, and some probabilities that tie them all together. And using this model, we can answer some questions about whatever phenomena we are actually describing. So let's take an example of this. Speech recognition. What we want to do is, given some waveforms, we want to figure out what is the thing that is actually being spoken. So in this case, you have a couple of different parts to your waveform, and you want to say that, okay, this represents dynamic. Okay. So how do we describe this phenomena using a hidden Markov model? So first thing we have are hidden states. Hidden states are things that represent the ground truth, and they're things that, as the name implies, you can't actually see. So in this case, it would be the syllables that you're trying to infer, dynamic. In addition, you have observations. These are the things that you actually can see, hear, or measure. So in this case, they're the waveforms. Okay, and so every hidden state emits some observation. Every syllable emits some sound waves. Okay. And we're going to describe the relationship between all of these things using a couple of different probabilities. The first one is what's known as the initial probability. So in this case, not every syllable is likely to start off a sentence, at least not in English. And so if you know something about English, you can say that you're most likely to start off a sentence with these syllables. Then you have a transition probability A. So given two states, you want to say what is the probability of going from one state to another. In speech recognition, that means given a particular syllable, what's the probability of ending up with another syllable? Again, with English, it's not like you'll have every pair of syllables with equal probability. And here's something that's really important, is that the probability of going from one state to another does not depend on where you came from. It only depends on the previous state. There are extensions where you might consider, let's say, 2 states before or 3 states. We'll keep it simple with 1 state, but the important part is you're only looking at a finite amount of information. Okay, that's known as the Markov property, and that's what makes this a Markov model. Next, we have an emission probability. So that says that given a particular state, what is the probability that you will emit a particular observation? So given a particular syllable, what's the probability that you'll get this particular waveform, right? So not every syllable will have all kinds of waveforms being generated from it, even with different accents and different speaking styles. And just like the transition probabilities, it's important. We don't care how we got to the state. We just care about what state we're at, and therefore what is the observation that comes out of that state. Okay. All right. I'm not monitoring the chat right now, but are there any questions?
Not yet.
Okay. Cool. All right. So what are some things we want to do with it, right? So we have described speech recognition using this model with these numbers. So let's say we have an initial probability, transition probabilities, and emission probabilities. And we actually have a set of observations or emissions. So in this case, the actual waveforms. What we want to find out is what is the most probable sequence of hidden states that resulted in exactly those observations. So in our case, what is the most probable sequence of syllables that caused that sequence of waveforms to be emitted? That's the question we're trying to answer. So why is that a hard problem? Well, let's take an example. We are looking at waveforms, and let's say we just want to look at a particular piece of the waveform and just try to make an inference. Okay, this one is ah, okay, ter. That's what we saw. Okay, so far so good. But then the next one is mo, bil. Something went wrong here. And why is that? Well, maybe ah ter makes most sense for the first 2 parts of the waveform, but if you take it as a whole, that's not really what you want. What you really want is automobile. But you didn't know that until you looked at the later parts of the waveform. And that represents a really difficult problem to solve, because if you are at a particular state, you've inferred something about the rest of the kind of speech up to this point. The question is, where do you go next? And based on the probabilities you have, maybe the most likely thing to do is go to auteur, but really you should have gone to auto. Okay. we could try something a little different. We could try every possible sequence of hidden states, but we'd have to try a whole bunch of different possibilities here in the very beginning. And then once you get to the next state, you still have to try a whole bunch of different possibilities, because you really don't know which one of those low probability paths that you're taking is going to lead to the answer that you really want. Okay. So if you think about this, this is a very classic exponential time problem, okay, if you were to explore every single path. But we're going to take advantage of something, which is the fact that we don't have to care about where we came from, just where we are at a particular point. And so we're going to do something in between the two extremes we've looked at. The two extremes being look at only one path or look at every path. So in this case, we're going to kind of, once we infer part of a path, then we're not going to look at anything before it ever again. The way to do that is reframe the problem. Instead of where do we go next, where did we come from? Okay. So in this case, you could have inferred otter or auto, but by the time you get to mo, you know that you want to continue from automobile. Okay. Let me formalize this. We're going to define a function, v, t, and x. And that says, what's the maximum probability of ending at a particular state at a particular time, given all the observations or emissions that you've gotten to. Okay. So let's take an example of that. If you're looking at time 1, right, or 0, whatever you want to think of it as, the initial state. Okay, you have an observation. How likely is it that the state was S? Well, first of all, you needed to get into state S in the first place, right? So you have that pi of S to say that you got into state S, and you had to emit Y from state S. So that's the emission probability of Y from state S. And these are independent events because you don't care where you came from, and you multiply them together, and that's your probability of ending up at state S at the first time step if you know Y is your first observation. Just pausing for a second to let that sink in. Okay, how about in the middle? Well, what can happen is if you want to get to a particular state S, there's a whole bunch of states you can come from. Any of the previous states, in fact, right? And it doesn't matter how you got to it, but all you care is that you ended up at one of those previous states. So that's why we're looking at V again, right? So V at the previous time step for each of those previous states R. And from R, we need to transition over to S. So we're using the transition probability from R to S. And we're going to pick the likeliest path to continue from. So we're going to maximize over all the possible R's. Finally, now that you've ended up at state S, you're just going to see how likely was it that you emitted Y. So you just use the emission probability from S to Y. Okay. So we just built up this relation based on the principles of hidden Markov models. Okay. So I'm just putting these equations here to reiterate what we talked about. But I want to point out a couple of things that are really interesting about these equations. The inputs to these equations are basically integers, right? The time step is an integer. And the state that you end up with, well, there's a finite set of them. And so you can just treat it as like an integer. And then the other part is the equation for V refers to itself. There's a base case, but there is self-referential. It references a different value of itself, right? So this is known as a recurrence relation. Okay. And these two properties, the integer inputs and the fact that it references itself, is very important to what we call dynamic programming. So if we were to just plug in the values into this equation and just keep going and calculating all of these values, it would take a long time because you would end up doing a lot of the calculations again and again. Instead, we're going to be smart about it. What we're going to do is we're going to lay out all of the values of V based on both time and state. So time on the horizontal axis and state on the vertical axis, right? And the important part we saw was that we had a base case. So at time equals 0, we can calculate those values without having any other values beforehand, just the probabilities. So we can go through and just fill out this table for the first column, and we're good. Once we get to the next column, when t equals 1, well, a particular cell will need to look at all of the different values in the previous column, okay? But that's okay, we just calculated those. And in fact, let's see, yep, we can just keep doing this procedure, right? We start at the very first column, calculate those values, and then go from left to right. And by the time we need a particular value, we already have it. Okay. And the other part is we only calculate any one value just once. So let's think about how long this takes, okay? We have t different time steps and s different states. So the amount of memory you're going to take up is just s times t. And the amount of time it takes, well, you have to fill out s times t values. However, in general, each of those values requires s different calculations, right? There's s different arrows coming out of the later cells. Okay, so I'll have a slide that shows that later. But once we've calculated all of these values, then we can just go to the very last column, figure out what's the very largest probability of ending at a particular state, and just follow these arrows back. Where did we come from in order to get to that probability? And that gives us the best path. So in this case, this would give us the right sequence of syllables that matches our observations. And like I said, the space complexity is just s times t, and the time complexity is just s squared times t, okay? If you're familiar with computer science notation, this is a formal way of saying that, but the important part is that it's not exponential in either of the inputs the way we had described it in the other option, which was try every single path, okay? So I want to give a second to let that sink in. Cool. So I just want to cover a little bit of code. I know this is a R meetup, but I don't actually have that much experience with R, but Python is known to be pseudocode basically, so we'll just go with it, right? So we're going to represent a hidden Markov model as those probabilities, right? The initial probability, transition probabilities, and the emission probabilities, and they're just basic dictionaries. And this is just a class that stores those values and also keeps the possible states around for easy access. Okay. We're also going to create a class that has two things. This is basically going to be the value of V that we we want, right? It's going to be the values that are in that table. But also we're going to have what was the state that got us to that maximum value, right? So again, going back to this, right? S1 at time 2, we were able to maximize that probability by coming from S1 at time 1, and that we were able to maximize by coming from S0 at time 0, right? So we're going to store both the value of that we're calculating as well as the state that we came from. And this is known as a back pointer. Okay, I'm not going to go over this in a lot of detail, but this is just saying go through that first column and just calculate the value of V, okay? And there is no back pointer for these cells because we didn't come from anywhere. And for the rest of the time steps, we're going to look at the current observation. We're going to go through all the states. We're going to try to find the maximal probability, right? And we're just going to figure out where we came from and store that as our back pointer. And that's our value for the current cell, okay? Again, not going through this in detail, but it's actually really just implementing the equations that I showed earlier. Okay. Finally, at the very end, we're going to take the possible states and we're going to try to find out at the very last time step what was our maximum probability from V. Okay. And once we have that, we just go look at the previous state, and there's our path. Okay. All right. And this will give you the path in reverse, so you need to reverse it. Okay. You would not actually implement a hidden Markov model this way. It's going to be, this is not optimized in any way, but I wanted to show that it's something that if you just think about the first principles, you can actually come up with this code to implement it and understand every step of the way. Okay, so what I'm going to do next is talk a little bit about some actual real-world applications. And the thing with real-world applications is that they're not really clean. They're not ready to be used as a hidden Markov model right away. So what we're going to do is we're going to talk about pre-processing data in order to figure out how to fit it into this model. So we talked about speech recognition, right? You might think, well, a waveform is this abstract idea. How do you actually represent it as observations? Well, what you do is you look at a 25 millisecond window and you do something like a discrete cosine transform and also acoustic modeling. So you use prior knowledge of how the human ear hears different sounds. And then basically you're coming up with a set of numbers. And so this is like a 10-dimensional vector that you're coming up with. And any possible 10-dimensional vector is one of your observations, okay? So those are your numerical observations. And then you do this every 10 seconds, and that's how you get a set of observations in a sequence.
Sorry, Avik.
Sure.
Someone asked, can you clarify in your drawing, in your example, what is observed and what is hidden?
Yeah, in this particular case.
Is it? I'm not sure if he's talking about example or the previous demo you had. The automobile, the automobile and automobile.
I see. Okay. So let me go back to that. Right. So in this case, right, what your observation is the individual waveforms in the way that I described later, okay? But it's basically little chunks of time, and whatever sound wave was emitted at that time, that's your observation. These syllables that I'm showing on the screen, those are the hidden states. Those are the ground state that you're trying to infer, Does that answer the question?
He said yes.
Okay, cool. All right. Cool. Okay, so this is, in the case of speech recognition, to figure out the actual observations, this is what we do. Let's look at another example. This is actually the example that I learned in college. But basically, if you think about your DNA, it's composed of these bases. Okay, there's 4 bases, each with a particular letter, A, T, C, or G. And what you can basically observe is what are the bases in the DNA. But what does it mean, right? So it turns out that these bases are used to code for different amino acids, which then code for proteins. And you want to figure out what are the amino acids that it codes for. And an interesting wrench in this is that in DNA, there are parts that are not actually used, okay? So there are parts where there's sets of 3, okay, 3 bases that code for a particular amino acid. And so you have E1, E2, E3, E1, E2, E3, and so on. And then you have these I's, which are basically, think of them as like comments in your code. They're not actually used. And to figure that out, okay, so this is called exons for the parts that actually do something, intron for the parts that don't do anything. So let's describe this as a hidden Markov model, right? First of all, what is our ground state? Well, our ground truth, I should say. The ground truth is this area of the DNA an exon or an intron? Okay, so it's going to be either. In fact, not just that, but in the exon sections, is it the first of 3, the second of 3, or the third of 3 in a triplet? Okay, so E1, E2, E3, and I are your hidden states, and you don't know what they are. And your observations are just the base pairs, or the bases, okay, A, T, C, and G. And it turns out that exons and introns have different probabilities of showing different types of bases, and that's why we can make inferences using a hidden Markov model. The last example I want to show is face recognition, okay? So you have a face, right? And what we're going to do is we're going to look at a particular horizontal slice of the image. We're going to do something called a particular transform, the KLT, and pick out the top coefficient. So basically, again, we're creating something like a 10-dimensional vector that describes that little horizontal slice. And these are the observations that we're going to be working with. And what we're going to use as our ground truth is, does this slice of the picture represent eyes or nose or mouth, right, or forehead and things like that? And so the state transitions in the ground truth can go from like hair, and it can stay in the hair region and then go to forehead, and then it can go to eyes, then nose, then mouth, right? And if that's the case, well, there's your face, okay? So again, the hidden states are which region of the face you're looking at. And then the observations are a description of that one horizontal slice of the image. And different regions of the face tend to have different types of pixels and therefore different observations that they emit with different probabilities. Cool. So this is all great if you already have these probabilities that we talked about. Okay, so we're looking at the forehead section and it's going to have these observations with high probability and these other observations are low probability. But how do you actually figure that out? And that's where training comes in. Okay, so if you have a bunch of different observations or emissions and you know what your ground truth states are, you don't know how they're related, but you know what they are. and you know, well, actually, that's all you know, right? Then what you want to do is find the parameters, the probabilities that we talked about that maximize the probability of getting those emissions. Okay, and you try with a whole bunch of different data sets, and there you go. You have a hidden Markov model that describes your real world data. I'm not going to go into that in a lot of detail, but the basic idea is that we're going to start with either a random set of probabilities or we're going to use prior knowledge. So in the case of speech recognition, we can actually use the knowledge of the English language. And then we're going to do something called forwards and backwards estimations, where we're going to do kind of like what we did with that V value, right? We're going to go, that was going in one direction. We're also going to go in the opposite direction and do some calculations. And then we're going to use that and we're going to update the probabilities based on what we got. Okay. So again, I'm not going into exact equations of how to do those updates, but that's basically the idea. And you just keep doing that until you're not really updating very much because you've converged to a good solution. And this is known as an expectation maximization algorithm. And for hidden Markov models, the specific one is called Baum-Welch, and that's the training algorithm that you use. Okay, so a lot of information there. So do we have any questions?
Feel free to type or unmute.
I'll just put this up. I am available on a bunch of different social media. Happy to talk about this. I also write about this type of topics in a lot of detail, so happy to go into more detail if people are interested.
Kevin wants to ask on some clarification on what is it about HMN that makes them a dynamic programming example?
Great question. So the crux of the dynamic programming philosophy that I guess I didn't talk about in detail was this idea of this table, right? Like if you were to go and do these calculations naively, you would keep calculating the same values again and again and again. But if you observe that there is a particular order in which you can do them so that when you need a value, it's already there, that is what dynamic programming is. Okay, it's understanding that there's a lot of overlap in the smaller parts of the problem that you're solving, and then solving them in the right order so that you only need to compute everything once.
Mm-hmm.
Cool. Great.
Yeah, I know you show a Python snippet on how do you track the states and probabilities. In R, it's usually tracked by list. The list is like a hash dictionary, the most similar format in R.
Got it.
Yeah.
I see a question about predicting, say, stock markets. I'm sure you could find some ways to do it. I haven't looked it up, but if you look for dynamic programming stock markets, I have actually seen something on that topic, but I wasn't sure if it was a hidden Markov model specifically.
What do we do if we don't know all the states?
Yeah, so this is where, I mean, there are limitations to this approach, right? The states that you define are going to be the ones that model your problem that you're solving. So in some sense, a lot of times the states are actually kind of something you come up with, right? So you will know all the states. It is what you decide you want to infer in the first place.
Mm-hmm. Yeah, this is used a lot in NLP, especially because for language, there's infinite number of possibilities and variations. So usually it's more about how you formulate the question and then probably put them into a HMM, but the formalization of the question is usually the most difficult step. Can you think of any situation where your assumptions about the problem might change and a dynamic programming solution would not be applicable?
Yeah, I can try to talk a little bit about that. There are some assumptions that we made in the hidden Markov model, of course, right? The biggest one being the Markov property, that we don't care about the history. If you start caring about all of the history, then this becomes much trickier. The real issue is that if there's not a lot of overlapping subproblems, right? So we broke everything down into a set of smaller pieces, and then we saw that if we were going to look at the same pieces again and again, and that's what enables dynamic programming. If there is anything that prevents you from looking at the same state again and again, then dynamic programming is not really applicable. But maybe it wasn't a hard problem to begin with, right? Yeah.
Why is it necessary to use this model if, can you see the question?
Yeah, I can see it. So is it states, probability of state transitions, and probabilities of emission? Okay, yeah, so let's go back to kind of our definition over here. Right, yeah, so you need the states, the hidden states. You need the set of all hidden states. You need the set of all observations. And you need the transition probabilities and the initial probabilities and the emission probabilities. So those 5 things define a hidden Markov model.
No more questions. Thanks, Avik, for your presentation. Usually I leave the Zoom open for another 20 minutes until like 8 if people want to chat. Yeah, so, oh, I saw one more question for Avik if you want to answer. How do I identify if HMM is a fit for my model, for my problem?
I mean, that's going to be tough. You'll have to decide if the assumptions needed for the hidden Markov model, namely the Markov property, are good enough for modeling this particular phenomena. It may be that you try it and then it doesn't work. That's how you figure it out. Yeah, that may be the best way sometimes.